In this video, we'll be talking about strategy for integration, that's section 7.5. As we've studied from the beginning of this chapter till now, we've seen that integration is actually more challenging than differentiation. Differentiation seems to be straightforward, one-dimensional. Given anything, can apply chain rule, quotient rule, product rule, whatever. No such things occur in integration, and there is no obvious techniques that you would use for any problem you see. Until now, we've applied different techniques to different kind of problems. For instance, we saw in section 4.5 that we reviewed when we started this chapter, that's integration by substitution, that we can actually solve problem like that when it appears like a function of another function. We also saw how to integrate by parts in section 7.1, how to integrate trig functions in 7.2, how to make trig substitution in 7.3. In 7.4, we saw how to integrate by partial fractions. But in this section, we present a range of miscellaneous integral in random order, and the main aim is to try to recognize which technique or formula to use to evaluate the integral. There are no hard and fast rule to any given integral or a method that applies to a given situation. What we may do or advise is to kind of like find a strategy that you may think is useful and easy for you. A prerequisite for applying a strategy is kind of like knowledge of basic integrals. Like if you can transform an integral to look somehow, then you know how to integrate that. The table below have like some integrals that we've encountered previously, except some of them. And I think you should know this, at least from 1 to 6 are really very obvious. I think you should know. 7 and 8 can be solved using a U substitution. We also solve like 9 and 10 are just like the reverse of differentiation. We saw how to do 11 and 12. 13 and 14 are kind of U substitution. 15 and 16 here really we didn't do them because we skipped the hyperbolic function section, so you may skip this. However, 18 and 19 are very obvious. We did this one also. You could do that. Like they are just the reverse of inverse function differentiation. Then 19 and 20, you don't really need to memorize this. I believe you can do 19 using integration by partial fraction, and you can do 20 using trig substitution. So you need to kind of like know that if you encounter integrals like this, you've seen them before and you can evaluate them. Once you are armed with these basic integral formulas, if you don't immediately see how to approach a given integral, you might want to follow this 4-step strategy. This is just kind of like a suggestion. As I said, there are no hard and fast rule to doing this. Now, the first strategy to get this done, actually, I made this video earlier, but something went wrong in the recording. So some of the things here have been written already. I'm just going to explain them. So the first strategy is to simplify the integral as far as possible. Sometimes some algebraic manipulation, trig identity may simplify the integral and make it easier for you to see how to integrate it straight up. For instance, assuming you have this to integrate and then you make a U substitution, you might get stuck. But if you multiply through, then you see that the product of this gives you this. When you integrate square root of x, you get this, and when you integrate x, you get s squared over 2 plus c, and that will be all. Like, that is just all. you're asked to integrate tangent over secant squared. Now, anything over secant squared is just cosine. That's like taking the reciprocal of secant, you just get cosine. So this can be written as tangent over cosine times cosine squared. But tangent is sine over cosine, so one of the cosine here cancels out the one below. This is just going to give you like sine times cosine. If I make the u substitution, if I let my u to be equal to sine x or sine theta, then my du is going to be cos theta d theta. Okay, I think I did that before here. My du is going to be this. So this integral here turns into integral of u du, and if you integrate u du, you get u squared over 2 plus c. That is sine squared of theta plus 2 over c. Another way to do this is to recognize that this in here is something as half sine 2 theta, and when you integrate half sine 2 theta, you're going to get something else, maybe in terms of cosine to negative 2 cosine over 4, which can be rewritten to be this. But anyhow you do it, you still arrive at an equivalent answer to this. I think one example I'm very particularly interested in is this example here. I think this occurred in your midterm. Now, if you start making a u substitution here, you may end up not getting the right thing, or maybe going in circles. But if you notice that you can always expand what you have above to get this, and then divide by x to get this. When you integrate, this becomes your integral, and it's kind of very easy here. Or you are given this function to integrate. Well, u substitution may not help, and no method may help here. But if you can expand this, you will get this. Sine squared plus cosine squared is equal to 1, and 2 cos x sine x is equal to sine 2x. So everything here just simplifies to this. If you integrate 1, you get x. Integrate sine 2x, you get negative cosine 2x over 2, and this will be the answer. So if you can simplify the function you're given, that may help a whole lot. The second strategy is to look for an obvious substitution. If you're given an integration such that you can find a function u equal to gx in the integral whose derivative is du g equal to g prime dx also occurs in the integral, or maybe a constant multiple of this occurs in the integral, and then you can just make the u substitution, and that will be all. For instance, in this, I can let my u to be equal to s squared plus or minus 1. This tells me that my du will be equal to 2x dx, which implies that my 1/2 du is equal to x dx. Well, I have x dx here, so this integral here becomes 1/2 integral of 1 over u du. So that would just be 1/2 ln of u plus a constant c. And going back to x, that would be 1/2 integral of s squared minus 1 plus a constant c. And that will be all. If you try step 1 or step 2, this first two strategy, and it doesn't work, then you may look at the form of the integral and see whether, one, it looks like trigonometric function. You saw that in section 7.2 we saw how to integrate trig function involving products of powers of sine and cosine, product of powers of tangent and secant, of powers of cotangent and cosecant. Then if that's the case, we use techniques that we learned in section 7.2. If we look at the integral, the function f, it's a rational function, then we may need to see if it's possible to integrate that by partial fraction. If the function contained in the integral is having powers of x, that's a polynomial, or maybe a transcendental function like exponential, logarithmic, trigonometric function, we may need to try integration by parts. Make choice of u and the v using the mnemonic we saw earlier. I think you should remember this. And then try integration by parts that we saw in section 1. If the function involves radical, particular kinds of substitution may be appropriate. For instance, if you have like square root of s squared plus a squared, s squared minus a squared, or a squared minus s squared, we saw in section 7.3 that we can actually solve these ones using trigonometric substitutions. If it's a radical involving like linear expression under the radical, we can use the rationalization or maybe substitution of u is equal to that radical expression and probably turn the equation or the problem to a rational function and then integrate by any method we know. Usually it could be by partial fraction. Now, if we try these first 3 methods and nothing works, then we may need to try again, because at first we may not have seen something that we see when we try all these methods. We try again. Try a substitution. See whether a substitution works. It may not be obvious at first, but with some ingenuity, some desperation, you may see an appropriate substitution that may work. Sometimes you may even be surprised what your mind may come up with. Another thing is to try integration by parts again. Sometimes it may not be obvious that we can use integration by parts to solve some problem. For instance, recall when we are solving the integral of ln of x, which we integrated to be, I think, x ln of x minus x plus a constant c. This wasn't obvious that you're going to use integration by parts here. For instance, imagine you are integrating inverse tangent of x. It's not obvious that you will need to use integration by parts. But if you try integration by parts here, it works, because if you use Layard, there is no log. Tan inverse is inverse tangent, so you could let your u to be inverse tan and the v equal to the x. Then your du would be 1 over x squared plus 1 dx and your v equal to x. Integrating by parts, your uv is x tan inverse of x minus v is x, du is this whole thing. So you get this. When you integrate this thing, this is what you get here, and that would just be it. It may not be obvious at first, but when you look a little bit more deeper and spend more time with it, you may see the that it could be integrated with by parts. We may also need to manipulate the integrand sometimes. Like if it's an algebraic expression, trig identity, you may need to rationalize or maybe do some transformation that may turn it into an easier form. This may be substantial sometimes and may involve some ingenuity, but with practice, you get used to it and it becomes like second place to you. So imagine we are asked to integrate the x over 1 over 1 minus cosine of x. If we multiply this by 1 plus cos x over 1 plus cos x, you see above we have 1 plus cos s, and below we're going to have 1 minus cosine squared of x. But 1 minus cosine squared of x is sine squared. So this is what we have, which simplifies to this. We know how to integrate this. If we integrate this, we get negative cotangent. And this one, we can use a u substitution to integrate this to get negative 1 over sine x. And that becomes our integral. Sometimes, if we try and it doesn't work, we may want to relate the problem to a previous one we've encountered before. With time, you get to build up your experience, and if one method doesn't work, you may relate it to one you already know or you've encountered before. Or you may even be able to express a given integral like entirely as a different one that you're used to. For instance, imagine you're asked to integrate tangent squared times secant of x. It may be challenging, but if you remember the identity that tangent squared is equal to secant squared minus 1, then we can write this to be this. When you multiply out, you get the integral to be this. We saw how to integrate this, and we saw how to integrate this, and like that you've seen that your integral becomes easy. You can use the result you have before, and that will be that. And finally, if it doesn't work, then it's possible you may just need to use several methods. You may need to combine 2 or 3 methods to evaluate an integral. For instance, you may need to combine trig substitution and u substitution. You may need to combine integration by parts and u substitution. You may need to combine trig integral and maybe integration by parts. Anything. Combine any number of methods that to help you to get the thing done, and if that helps, it should be good. In the next video, we'll be looking at some examples that we can apply this. I may not be able to solve all the problems in details, but I'm just going to tell you strategies to use if you encounter such integrals. So this should be all for this video.